Hey guys, welcome to our first video lesson. Today we're going to talk about the difference quotient. Watch this one prior to class on Monday. All right. Say we've got some function f of x, and consider that for some reason we want to know the average slope between 2 points on that function's graph. Well, we could think of this as connecting those 2 points, and we call that connection a secant line. So what we're looking to do here is we're looking to find the slope of that secant line, that is the slope between 2 points, the average slope over a graph, over some chunk. So how could we figure that out? Well, if the first point is x1, y1, and the second point is x2, y2, and we're looking to calculate that secant line slope, then it's as simple as just using the good old formula for average slope. y2 minus y1 over x2 minus x1. I guess it's not the average formula for slope, it was just the good old formula for slope, but now we're turning it into the average formula. So y2 minus y1 over x2 minus x1, the change in our height divided by the change in our horizontal location. And that works pretty well, except we can actually simplify this a little bit. Since we're working with a function, we can use that function to our advantage here. So let's call that leftmost horizontal location simply x. Then, if the rightmost location is h ahead of x, we say that it would be at x plus h. Okay, so because vertical height on a function is given by the output from our inputs, we get that our heights are going to be f of x and f of x plus h from the respective inputs. So our points are converting as follows. x1, y1 is converted into x, comma, f of x, and x2, y2 is converted into x plus h, comma, f of x plus h. So now that we've got that, we can calculate our secant lines with our new locations, and we've got that our average slope is the change in the heights, f of x plus h, minus f of x, divided by the change in our horizontals, x plus h minus x, and that simplifies pretty nicely to f of x plus h minus f of x over h. We dub this the difference quotient, and we're going to talk about it quite a bit over the next couple days. So the difference quotient gives us a clear formula to find the average slope between some location x and another location that is h ahead of that x location. All right, let's try an example out so we can take our brand new difference quotient out for a spin. Say we've got the function f of x equals x squared minus 3x, and we're considering slopes based off that starting location x equals 1. So we've got some starting location, and we're considering what are the average slopes to different places from that starting home base x equals 1. So what if we've got a width of h equals 2? We can see that on the picture there, what it would be if we drew it in, but what is the actual value for that slope? So our difference quotient, average slope equals f of x plus h minus f of x all over h. We know what our x value is. Our home base is 1. We know what our width is, 2, so we just plug them in. F of 1 plus 2 minus f of 1 all over 2. And then we've got f of 3 minus f of 1 over 2, right? We're just plugging in x, plugging in h, simplifying a little bit. At this point, we now actually need to apply our function. Our function is x squared minus 3x, so we've got to apply that to f of 3 and apply that to f of 1. Applied to the f of 3, we've got 3 squared minus 3 times 3, and then minus, and make sure to wrap that next part all in a quantity, because it has to be in a quantity because it's minus that entire other function. So minus all of f of 1, so it has to be minus quantity, so either large brackets, large parentheses. Just make sure you don't ever forget to subtract that entire other portion. All right, so f of 1, 1 squared minus 3 times 1. We can simplify that a bit. 3 squared minus 3 times 3, 9 minus 9, that's 0. And then 1 minus 3 is negative 2. So we've got 0 minus negative 2. The negatives cancel each other out. Positive 2 over 2, which simplifies to a nice positive 1, which makes sense. That's basically what we see on our graph. All right, let's try it again with a different width. What if we've got width h equals 1? Well, our average slope is going to be f of x plus h minus f of x over h, right? Just the difference quotient. Plugging in now, we've got f of 1 plus 1 minus f of 1 all over 1, right? Our h value is changing around, but everything else is the same. F of 2 minus f of 1 all over 1. We plug into that, and now we've got 2 squared minus 3 times 2 minus 1 squared minus 3 times 1. Notice how the f of 1 part stays the same every width we have. Since we're keeping our home base at the same place, right, we're not changing off of that home base location x equals 1, that part is going to always be the same. So if you do multiple widths, if you've got multiple widths that you have to do for the same problem, just remember that value and you can just keep putting it in each time as opposed to having to recalculate it if it's difficult to calculate. Anyway, f of 2, 2 squared minus 3 times 2, just applying our function, minus quantity, 1 squared minus 3 times 1. So 2 squared minus 3 times 2 is 4 minus 6, so we get negative 2, minus the other one, negative 2. Negative 2 minus negative 2, that's negative 2 plus 2, so 0, 0 over 1, we get 0, which once again matches up exactly what we see from our graph. Finally, what if we've got a width of h equals 0.5? We apply, once again, the difference quotient, so it's f of 1 plus 0.5 minus f of 1 all over 0.5. Remember, don't forget to change that h on the bottom as well, even if you're doing a bunch of these. So f of 1.5 minus f of 1 divided by 0.5. We apply our function. We have 1.5 squared minus 3 times 1.5 minus, same thing that we keep having, 1 squared minus 3 times 1 all over 0.5. I won't do all the arithmetic here because, just break out a calculator for it, but we ultimately get negative 0.5. Once again, seems to make sense from what we're seeing in our picture. All right, so that basically wraps things up for this video lesson, but here's an interesting thought to ponder. Notice that as we shrunk that h to smaller and smaller values, the slope it gave started to better and better approximate the slope at our home base of x equals 1, right? As we got that h smaller and smaller, as the width went down farther and farther, we started to get a better sense for the neighborhood slope, right? What the slope was in the area around our home base x equals 1, where we were sort of setting things off from. So that's a really interesting thing to notice, and we're going to run with that tomorrow. So just think about it for a little while. We'll really get into that part tomorrow. All right, thanks for watching the video lesson, and I'll see you tomorrow. Bye.